Okay, so let's see what we have. All right, so we have four variables. First variable is position. Obviously, that's the kind of work that that particular person does. Second variable is, let's see, age range. It's a categorical variable. It's ages, but the ages are broken up into categories. And I can see one category is 18 to 30, and it looks like there's 31 to 45. So it looks like there's at least two, maybe three or more categories. Next is years scale. I guess that's years of experience, for instance, 6 to 10, 11 to 15, and so on and so forth. And then finally, there's the hourly wage. So it looks to me like we can do a lot of stuff with this. We can evaluate if there's a relationship, if there's an association between the type of position that these people have. Let's go to variable view, type of position that each person has. And let's see, oh, they're all nurses. Some of them are office nurses, some of them are hospital nurses, I presume doctors' offices. We're looking at their age ranges, their years of experience, and their hourly salary, and we're comparing them. We're trying to see if there's an association, say, between what age range that they're in and how many years of experience they have. If there's an association between the type of nurse, type of nursing they do, office or hospital, and their, say, their salary, or maybe we could even look at whether or not there's an association between the type of nurse and the age range. Perhaps younger nurses tend to work at hospitals, and older nurses tend to work in doctors' offices. Who knows? We can actually take a look at that if we want to. Okay, so and in fact, in that case, we'd be looking at two categorical variables. Nurses has two values, 0 and 1 for office and hospital. And age range has three values, 18 up through 65 in three groups. So that would be categorical. So we would use chi-square for that, that particular situation. For years of experience, also a categorical variable. If you wanted to see if there's an association between the age range and the years of experience, you would think so, right? Older nurses, I'm sure, probably have more experience. That would be again a chi-square. That would be a 3 by 6 table, kind of a big chi-square, right? So, but it would be, we could examine it as a chi-square. But probably the thing we would spend the most time looking at is we know the average salary, and the average salary is a numerical variable. These are wrong here. These values here for position, for age range, for years of experience, they are all nominal variables. So I'm going to make sure SPSS realized that they're nominal variables. Now the salary, however, was a numerical variable. Notice it's not coded with the values. Okay, it's a numerical variable. So in that case, I could compare whether or not the average salary for nurses who work in an office versus a hospital is different. I can look to see if salary changes over a period of time, if the average salary is different for different age ranges. Now there's three age ranges. Let's see, the nurses, there were two types of nurses. I could find the mean of both of them. So gee, that would be a t-test that I would be performing there. As far as the age range is concerned, there's three groups there. So I could compare the average salary for each of those three groups to one another. But since it's three groups, I would avoid using a t-test in that case. So I would use analysis of variance. And then finally, if I wanted to compare the nursing type to the age, those are both categorical. I'd use chi-square, and maybe odds ratio, a little bit more odd there, but we could use odds ratio because it's a 2 by 2. Oh, no, it's a 2 by 3 table. I'm wrong. We wouldn't be able to use odds ratio unless we recoded some of it. Okay, and finally, let's see, can I use a correlation or regression? Well, I only have one numerical variable. We haven't really talked about logistic regression yet, so for now, I'm not going to be able to do a linear regression on this data since I only have one numerical variable. But let's play with what we already have. Let's try those different kinds of analyses. Okay, so first thing I'm going to look at is whether or not office nurses and hospital nurses make the same amount of money, or one makes more than the other, the average salary for one is more than the other or the same as the other. So my null hypothesis is that the mean salary for office nurses is equal to the mean salary for hospital nurses. My alternative hypothesis would be that they're not equal. So I'm working with a nominal variable, and I'm working with their hourly wage, which is a numerical variable. So I'm going to use our t-test. So I'm going to say analyze, compare means, independent samples t-test, right? Two independent samples, hospital nurses and office nurses, independent samples t-test. My test variable is going to be my average salary. I'm going to move that in there, my numerical variable, which is salary. And my grouping variable, I'm going to break this up into two groups, which is the nursing type. And that's going to be either general nurses, hospital nurses, or office nurses. Now it asks me to identify which is which because although we see them as as office or hospital, they are actually represented here by the numbers 0 and 1. So I'm going to click in here, and I'm going to click and enter 0 and 1, so we know SPSS knows those are the two groups that we're going to use. By the way, I didn't realize until right this very minute that when you had these entry boxes open, you could actually go up here and turn the value labels on and off without having to close those boxes. Very convenient. Nice discovery. So I'm going to click continue. And I'm going to go ahead and click OK. The options generally are set up by default the way we probably want to use them. So our output is going to perform an independent samples t-test. And as usual with an independent samples t-test, we get a t-test first we get some descriptive statistics. The mean salary for hospital nurses is $20.67 an hour, 68 cents an hour. For office nurses, it's $18.70. Very old data. It's changed quite a bit, right? Nurses are doing a lot better nowadays, right? Because they're really in demand. They do a lot of work and they do good work. And they're needed. So hospital nurse, you don't get off cheap hiring hospital nurses and office nurses anymore. So let's see, standard deviation is kind of similar, right? It's very similar, although it's a big sample size, so maybe they're not similar enough. And in fact, it looks probably most of the time, as Professor Weicker suggested, we're going to use this bottom version of the t-test. I'm going to ignore this. This is not part of our actual t-test. These lines are. I'm going to use the bottom one. In fact, your result won't change anyway. A few numbers will change, but your result won't change. So if I use the bottom version of the t-test, t is equal to 11.879. That's a very large t-value. That's the number of standard errors apart that the two means are. Right? You can see the standard errors are very small there because such a large sample size. Right? So let's see what we have. Well, our significance, our p-value, is less than 0.001. So it indicates 0.000, right? That's far less than 0.05%, which is what we would want to not exceed before we rejected the null hypothesis. So we can go ahead and reject the null hypothesis because our p-value, our probability of being wrong if we reject the null hypothesis, is less than 5%. Another way of phrasing it is that the probability we would get this extreme a difference, this number of standard errors apart, this extreme a difference, 0.000 or 11.87, the probability we get that extreme a value when the null hypothesis is true is very unlikely, certainly less than 5% chance, which is our limit for our acceptable error. So we would reject the null hypothesis. The other way I know I can reject the null hypothesis is that if we look at the difference in the two means, we would expect if the null hypothesis was true, that there's no difference in the two means, that the two means are different, the two means are the same, then we would say, well, the difference in the two means is equal to 0, right? Well, in this case, we have a 95% confidence interval for the difference between the two means. And we're 95% sure the difference between the two means is between 1.66 and 2.32. So we're also 95% sure that it's not zero, because zero is outside of the confidence interval. So another piece of evidence that we could reject the null hypothesis. Okay, we use the data in a way that would enlighten us as to the comparison of these two means. A categorical variable, numerical variable, led us to use the t-test. Okay, so let's go back and take another look at this. Okay, now the other thing we have here is office nurses and the age of the office or hospital nurses, and the age groupings of the nurses. Let's see if there's an association between whether someone works in an office and what age group that they might be in. Whether it's likely that for some reason that there's an association between these, that perhaps older nurses tend to work in one environment, and younger nurses tend to work in another. So I'm going to go up here to analyze. I'm going to say, let's see, analyze, and I'm going to say, let's see, cross descriptive statistics and crosstabs, right? Because I need to organize the data first. And I'm going to put the nursing type in the rows, and I'm going to put the age range in the columns. Maybe not. Let me think about this. I think I might do it the other direction. Okay, whoops. Let's put the age range in this direction so that we can see if you're in a certain age range, what's the probability that you would work as an office nurse or a hospital nurse. That should be interesting. Okay, so I'm going to go ahead and just say okay. And when I say okay, because in cells only observed is checked, it's just going to create that crosstabs table for me. I'm going to click OK. See what I get. Here's our crosstabs table. There's 3,000 nurses that are in this data set, no missing values. And let's see how it looks. Well, 18 to 30, we have 320 nurses out of 480. 31 to 45, we have 1,000 out of 1,600. And 46 to 55, we have 592 out of 888. It's kind of hard to interpret here, isn't it? Okay, so let's get a little bit more information out of this. This time I'm going to go to Analyze, Descriptive Statistics, Crosstabs. Now you could do this all at once you're actually doing this, so you don't have to kludge around here the way I'm doing. So I'm going to click on Cells. Now notice, I could, if I wanted to know the expected values, I could click on that. And I could click on Percentages by Rows. I'm going to do those two. I'm going to click OK. So now when the table comes up, not only do I have my actual count, but I also have the number I would have expected if there's no association between age and the type of nursing work, the type of environment that a nurse would work in. And let's see, for the youngest age range, well, gee, it looks like we got exactly the range that we would have expected. Overall, 67% of nurses work in hospitals and 33% of nurses work in offices based on this sample, right? We'll never know exactly the proportion of the population, but based on this sample, that's what we're led to believe about the population, right? So 67%, and in fact, for this age range, 18 to 30, wow, it's exactly 1/3. The actual count, the actual values, or the observed values is 320, and our expected values, because we would have expected if there's no difference in based on the age groups, there's no difference in the rate at which you would work in a hospital, we would expect all of them to be 2/3, right, of the total for that particular group. Okay, it is for this one. Let's take a look at the next one. We would have expected 1,088. Our expected count was, I think there's something wrong with this data, 592. I don't know who made this data up, but unfortunately, wow, look at that. I fell into a real trap there, right? I don't where did I get this weird data? That's amazing. I pulled this up from one of the 9,000 texts that we used over the years, and a lot of them had sample data. So this is not so good. It's not such a good one. I am going to analyze descriptive statistics, crosstabs. I'm going to go ahead anyway and run my chi-square. I'm going to click on statistics, and I'm going to go ahead and click on chi-square. I'm going to click on risk also to calculate my odds ratio and my relative risk. Okay, and I can see right now that my relative risk is going to be 1 because they're all 2/3 over 2/3 over 2/3 and so on and so forth. The only problem is it's not even going to bother to calculate risk because in order to calculate odds ratio and risk, you normally would do that only with a 2x2 table, not with a 2x3 table. We can get around that. Maybe at some point, if we have time, we'll do that now. If not, I'll make sure that we go over it on Saturday morning so you can see how to manipulate the data so that you can do an analysis of something that gives you more values than the 2x2 table, but still find a way to get the advantages of getting a relative risk or an odds ratio out of it. So I'm going to click continue. I'm going to say okay. And our chi-square I don't think is going to make it, right? In fact, our chi-square is equal to 0. And our significance, our p-value, is well over 0.05. So there is no association. In fact, in this bizarre data, it doesn't matter what age range you're in, you're working in a hospital versus an office at exactly the same rate, no matter what. And boy, weird data. Okay, so had there been differences here, we would have gotten a chi-square that was different than 0, right? We expected 0 now because of the data result that we saw when we looked at the observed values. Okay, we would have gotten something that was different than 0, a chi-square of 0, and a different p-value. And if the p-value was small enough, less than 0.05, we would reject the null hypothesis. Our null hypothesis was that there's no association between the age range and the type of nurse, where a nurse might work, and I'm about to tell you why this didn't work. I just realized it now, and the type of work that they did. There's no association between them, and the reason why there's no association, that there's no association between one or the other. In other words, nothing that would show us that one would influence the other or change the other, is because we're talking about the same nurse. Okay, so in other words, this nurse works in an office and they're in this age range. This works in an office and they're in this age range. I should have realized that as soon as I looked at the data. So this is all the same nurse. That's why we got such a silly result there. So let's look at this differently now. Let's look at this to see if office nurses, let me see, can I do this now? Let's see if office nurses, actually, age range, yeah, I would have thought they shouldn't have been the same number, right? Some of that you would expect that office nurses, they could have been in different age ranges, each one of these. I would have expected something different. Somebody did a real bad job with this data. Okay, let me just do a quick analysis here. Just see if I can get a difference here. Cross tabs. But this time I'm going to do type of nursing position and the years of experience. See if I can get something out of this anyway. Okay, let's do this. Let's go ahead and take a look at this from another perspective. Okay, this time I'm going to take a look at two categorical variables here: the nursing position and whether and how many years of experience that they have. So, is there an association between whether a nurse works in an office or hospital and the years of experience in nursing that they have? Perhaps a lot of nurses start in hospitals and then move on to offices and so on and so forth. So, our null hypothesis is that there's no association between the age range, and the type of position that you would hold, either in an office or in a hospital. Okay, so younger nurses would hold positions in an office at the same rate that older nurses would hold position in an office. This is the null hypothesis. The alternative hypothesis is that there's a difference in that rate. So let's go to Analyze, Descriptive Statistics, Crosstabs. This time it should work. Okay, and I'm going to put In my rows, I'm going to put the years of experience. Okay, and in the columns, I'm going to put the type of nursing that they do. So we can get a look at the rate at which nurses in a certain age range work in an office or a hospital. In my cells, I'm going to leave observed values just so I can check I don't get any funky results like I just did. And I'm going to get percentages by rows so I can see the percentage of nurses that work in a hospital or work in a office for each one of the three age ranges. And I'm going to ask it to give me a chi-square. I'm going to turn off risk because I know it's just going to give me a warning that it can't do it for a 3x2 table. So I'm going to click OK. And let's see what our result looks like. Okay, so our for 5 years or less of experience, our expected value is 150. Excuse me, our actual value is 150. Our expected value for those is 151. In other words, we would expect 66% of nurses to work in a hospital and 33% to work in an office. And in fact, it's a little less than 66.7%. It's 66.1, so it's a little less than we would expect. Well, let's take a look at the next. Oh, there's a lot of groups here. Let's take a look at the group 6 to 10 years of experience. Well, in that one, it looks like it's almost right on the money. With the next one, it looks like a larger percentage of this group with more experience tends to work in a hospital. Let's take a look at the next one. 16 to 20 is 64%, a bit less. 21 to 35, 64%, a bit less than we would have expected. And finally, for 36 to very experienced nurses, a big bunch of them appears to work in a hospital compared to the percentage that works in an office. Okay, so let's see if we can see. First of all, number one, I'm a little leery of this data because let's see, as they get more experience, 66%, 67, 68, 65, 67, 70. It looks like it tends to climb. I have a little bit of an issue here in the middle here, but for the most part, the percentage of nurses working in a hospital increases as they get older, except for a couple in there that kind of gave me a weird result. So let's take a look at our chi-square value. Well, our chi-square value is 5.5. Our null hypothesis, again, was that there was no association between years of experience and whether a nurse worked in a hospital or office. Well, 5.5 for 5 degrees of freedom. How do we get 5 degrees of freedom? 1, 2, 3, 4, 5, 6 category, 6 rows, right? So 6 minus 1 is 5, and 2 columns. 2 minus 1 is 1. 5 times 1 is 5 degrees of freedom. So 5.562 for chi-square and at 5 degrees of freedom gives us a p-value of 0.35. So our null hypothesis is that there's no association between the amount of experience and whether or not you're likely to work in a hospital or an office as a nurse. And since this is greater than 0.05, I fail to reject that null hypothesis. So I can't say that there is a difference. I can't say that there's an association between age and working in what work environment you would work in for these nurses, right? So I failed to reject the null hypothesis in this case. At least we had data that let us get some numbers out of this thing this time. Okay, so let me move on. That's chi-square, kind of a funky data set there. Let's move on to another data set. So we did a t-score, and we got a analysis of a chi-square. We didn't do odds ratio because it wasn't a 2x2 table. Let's see. I think I might have something here we could use for analysis of variance. Let's check if there really is. Okay, so in this data set, what do we have? We have variables. Let me just check if there's any questions there. I've been encouraging you guys to post questions to Blackboard, so I know kind of where you're struggling, and because I have to guess kind of if you don't give me some feedback and tell me, gee, I really don't understand this part of this stuff and this is really complicated, that's hard for me to get. I have a little bit of experience with it, So I can somewhat guess what you might be having a hard time with, but it helps if I get some feedback and know. So if you want, or if you have an area of concern, post it to the discussions forum in the particular forum section, which is for online review questions, and I'll make sure I get to them as I work. Okay, so let's take a look at this one. In this one, we have four variables again. We have. Let's see what we have here. Well, we have a, a variable called. Oh, well, excuse me. I got to open the same one again, didn't I? Whoops. There. Is this the one I want? Okay. Position. Nope. I don't want that one. No. Okay. Yeah. Let me get rid of this. Let me close this out. No, I don't need to save that. No. Hourly wage. Total cholesterol by education. Okay, let's open that up. Oh, I could have done analysis of variance with that also, couldn't I? Let me pull that back up again. Okay, let me take a look at this once more. Let's take a look at our nurses again. Okay, one of the ways I could have looked at this is I could have evaluated. I need to bring this back. I didn't save this, so it didn't save my changes for nominal variable there. Okay, those are nominal variables. We know that position is 2 values and age range has like 6 values and so on and so forth. So let's see if there is a difference in the average wage based on the years of experience. How many columns are there? How many values are there for years of experience? Well, there's 6. So I would think that there's going to be a difference between these different categories of age and how much the average salary for nurses in each of those groups is going to be, right? So let's take a look at that. Let's analyze that. Well, if I want to compare means, the average salary, the scalar variable, numerical variable, which is hourly wage. If I want to compare the mean hourly wage for office versus hospital nurses, I use the t-test, which we just did before. But if I want to compare the average salary for nurses who have 6 to 10 years of experience to nurses who have 11 to 15 years of experience, if I'm only going to look at those two, I could use the t-test. I would do that by saying, well, first, let me just go over here and go into the value menu, turn off these values. Oh, and look, it looks like those are 1 and 2, the values for those two variables, right? So I could go to Analyze. I could go to Compare Means, Independent Samples t-test, and even though put my hourly salary in the test variable, put my years of experience in the grouping variable, and even though it's 6 values, if I'm only interested in comparing 2 groups, I could just put 1 and 2 in here. And it'll only look at those 2 groups, compare those 2 groups. Okay, and sure enough, I do my t-test and I get a significant result because apparently there is enough of a difference between nurses. My null hypothesis would have been nurses with 5 or less years of experience make the same amount of money as nurses with 6 to 10. My alternative hypothesis is that they're different, and since my significance for my t-test, negative 2.87, is less than 0.05, I can reject the null hypothesis and say, indeed, they do make a different amount of money. Not a whole lot, right? $18 versus $19, but it's a statistically significant difference. I'm 95% sure, less than 5% chance of being wrong if I reject the null hypothesis that the two means are the same. Well, that's good if I want to just compare 2 groups out of that. Or if there are only 2 groups to start off with, I could pick out a different 2 groups. But rather than do that, is going to involve a lot of error, introduce a lot of error. So instead, if I'm interested in comparing multiple groups according to their average wage or salary, in other words, my null hypothesis is there's an association between the years of experience and the hourly wage for nurses. And my alternative, that there is no difference; they're equal. And my alternative hypothesis is that there is a difference between the average wage for nurses in different age group, experience groups, and their average salary. In order to solve that, I'm going to go with I'm going to go with analysis of variance. Why am I doing that? Because I could do multiple t-tests to compare all the different ways of examining this, but it's going to introduce so much error that it's not really going to be valid, because eventually, if I'm only willing to accept 5% chance of error, if I run it repeatedly, it multiplies or increases my chances of being wrong if I reject the null hypothesis. So instead, I'm going to use analysis of variance. Analyze, and I'm going to say compare means, because we are still comparing means. One-way analysis of variance, and I'm going to put the hourly salary up in here because that's what we're finding the mean of, and I'm going to put the years of experience into the factor. Now notice it doesn't ask me to put the 1 or the 2 or the 2 and the 5, because I'm not comparing two groups like in a t-test. I'm examining all the groups at the same time. I'm going to click OK. My output window is going to come up again, and look, it calculated, as we did in class, as we did in some of the other exercises. It calculated the sum of squares, the degrees of freedom, so it gave me a mean sum of squares, a measure of variability between the groups, between the means, and it gave me a variability within the means, sum of squares, divided by the degrees of freedom, which is 15. So my analysis, my F statistic, or my analysis of variance statistic, is 39. Now, it's going to depend on the degrees of freedom that we're going to be interested in. For this is 2905, this is 5. So we normally, if we weren't using SPSS, we would have to go to a table to look up the critical value to see if we reject the null hypothesis. But SPSS gives us a p-value for this F statistic given these degrees of freedom, and the p-value is less than 0.05. So I can reject my null hypothesis that the mean for teachers who have 5 years of experience, 10 years of mean is equal to the mean for 10 years of experience, is equal to the mean for nurses who have 15 years of experience, is equal to the mean. I can reject my null hypothesis that all those means are different and accept my alternative hypothesis that at least a couple of those means have to be different. Maybe not all, but at least a couple, right? At least two have to be different. So now that I've demonstrated at least two of the means are likely to be different at this level of certainty, I can now go and do some post hoc tests, test which of these comparisons, these means, are likely to be statistically different. Compare means, analysis, one-way analysis of variance, and then this time I'm going to click into post hoc, and I'm going to choose typically Bonferroni, Tukey, or LSD. I'm going to choose Tukey. Okay, that's a relatively conservative test. I'm going to click continue, and now SPSS is going to compare each permutation of these outcomes. In other words, it's going to compare 5 years of experience to 10, 5 to 15, 5 to 20, 5 to 30, and 30 to 15. Every permutation that you can possibly have of these 5 or 6 different values. I'm going to click OK, and let's see where I stand. Okay, so here, if we compare 5 or less years of experience to 6 to 10 years of experience, well, 0.065, that's not statistically significant, not less than 0.05. However, there is a statistically significant difference between 5 and 11 to 15, or 5 and 16 to 20. In fact, 5 and any of the other more experienced levels of experience for these nurses. Okay, how about 6 to 10? Well, let's see. Except for comparing it to 5 or less, 6 to 10 is different, statistically different from all the other groups, and so on, and so on. And then we have one that is not. 21 to 35 is not statistically significant different from 30, 36 or more. Looks like maybe wages stagnate over there, between, which is not that surprising, is it? Right? That like within that age group, within that level of experience, that your salary may have peaked, and it's difficult to get a higher salary with more experience. Right? So though in those cases, for 21 to 35, we failed to reject the null hypothesis that there's a difference in the average salary, and for 5 or less versus 6 to 10, we failed to reject the null hypothesis that there's a difference in the average salary. But for the rest of these comparisons, there indeed appears to be a statistically significant difference in the average salary. Okay, so that's our analysis of variance. Okay, so let's move on to correlation and regression. Let's see if we can't find something that has a couple of numerical variables. Okay, and remember, we're doing this. What we're doing is we're looking at these data sets, and we're trying to determine how we might analyze these using what kind of statistical tests we might use to analyze these different data sets based on what kind of variables that we're encountering. Okay, so let's take a look at slugging percentage and altitude. Okay, good. Let's see. Let's a baseball one. And I'm going to go to the variable view. And let's see. In the variable view, we have city. Okay, actually, there's stadiums. They're actually the locations where they play baseball. And we have, for each one of those, we have the altitude of the stadium. Baseball, people who like baseball tend to be like really interested in the statistics of the game. Everything from the earned run average to the batting averages to what's happened historically in baseball and so on and so forth. So they're really consumed with the statistics of the game. So in this case, there's a lot of people that say, gee, in stadiums that are at high altitudes, like say in Denver, for instance, the ball carries better. So it's easier to hit home runs. Okay, so we want a measure of whether or not it's easier to hit from multiple bases or home runs in certain stadiums based on the altitude. Is that really true? Is there an association between the elevation and how lively the ball is, or how easy it is to hit home runs in those stadiums? So we don't have home runs. We have something else. A statistics called slugging percentage. And I used to know what that is. I'm a little bit of a baseball fan, but I used to know what that is. I think it's got something to do with a combination of number of home runs and extra base hits and RBIs and stuff like that. Let's see if I can't find it. Slugging percentage. Yeah. Okay, so that it does. The measure of batting productivity is calculated as total bases divided by the at-bats through the following formula: at-bats. So in other words, it's influenced by home runs, but it's not just the number of hits you get, but how many bases those hits account for. So doubles and triples and home runs will boost your slugging percentages. So if you have a high slugging percentage, it means you're probably getting a lot of extra base hits and home runs. So now the argument is that maybe that's associated with the altitude of the stadium. So we have two numerical variables here. We have the slugging percentage for all batters that bat in that stadium, and we have the altitude of those stadiums, I presume in feet. So we have a numerical variable for slugging percentage and a numerical variable for the altitude. So let's see if there appears to be an association. So one of the first ways I might look for an association is I might look for it graphically. Let's do a scatter plot. Legacy Dialogues, scattered plot. And I'm going to say, let's say a simple scatter plot. And I'm going to say in the x-axis, I'm going to put altitude, and in the y-axis, I'm going to put the slugging percentage, and I'll click OK. Okay, so let's see what we wind up with. Not very easy to interpret, eh? So yeah, not getting much help here. Let me do it the other way. Maybe it'll be a little easier to see if I do it the other way. Graphs, legacy dialogues, scatter dot. Let me reverse them. It really doesn't affect the values, but maybe it'll make it a little easier for me to see. Okay, at least it'll be along the bottom. Okay, so if you notice that we have look at this the altitude there. It's hard to tell. Let's see. Slugging percentage is much higher at this higher altitude. Wow, it seems like such a outlier, doesn't it? Of course, it's much higher elevation too than the other stadiums. I'm going to do this two ways. Okay, so I'm going to go in here and I'm going to say, well, I'm going to go in here and I'm going to ask it to fit a line to that. And look, if I don't take that as an outlier, it sure looks like there's an association between the two of these, right? So I'm going to go ahead based on that, and I'm going to calculate a correlation coefficient. Say analyze, okay, and where am I going to go here? Correlate, bivariate, there's two variables, and notice it's going to wait for me before it gives me the okay to put two variables in there. And then I can say okay. And it will calculate a correlation coefficient. And look at this. Beeson's correlation coefficient tells me that the R value, the correlation coefficient, is a positive 0.486. And the probability of that being significant, in other words, not being zero correlation, is better than 0.05, is less than 0.05. So I can reject the null hypothesis that the R value is zero, in other words, no correlation, and accept the alternative hypothesis that there is a correlation, right? That there is an association between slugging percentage and the altitude in the stadium. So very interesting that we wound up with that, right? So now I could go ahead and I could calculate my my regression equation. In other words, describe that line that gives us a best fit. But I'm very uncomfortable with that outlier, that 5,000 feet. I want to take that out of the mix and see if it affects this. And I suspect it's going to have a big effect on that. So I'm thinking that's Denver. So let's go in here. There's a couple of ways I could do this. One way is I could filter out Denver. The other way is I could just tell it to remove Denver from this list. Notice how much higher the elevation is. Okay, so I've taken out that potential outlier. So let's do our graph again. Analyze, legacy dialogues, scatter dot. Let's do it without Denver now. Okay, and I have my axes already set up. And let's see, wow, it's a little bit harder to see now, isn't it? Right, although maybe, I don't know. Let's see if we get a correlation here. Okay, and I'll get my best fit line. And, well, it looks like there might be an association, right? But let's see how strong an association there is. Let's calculate that R value now. So I'm going to analyze. I am going to go into correlate, bivariate. And now I'm going to go ahead and do the same correlation, but without Denver included there. And if I do it without Denver, well, let's see. The correlation coefficient is positive. There's a positive association, it looks like, 0.190, right? Not as strong as it was before, right? Oh, but my goodness, it's no longer statistically significant. I can't say that this R value is not there by chance. So I can't reject the null hypothesis that the correlation is really zero if I exclude Denver. So it's a little bit sloppy. So I'm not going to go into regression on this particular set of data because I really dislike the fact that Denver was such an outlier here. So I'm going to do something else. Let's see if we got another piece of data here we can work with. And let's see, we have total cholesterol. This one we have, let's see, that's going to be analysis of variance. Let's see if I got something with a couple of numbers in it. Inflation. How about violent crime? Okay. I think we might have worked with this data set before, maybe not. Okay, so let's see what we have here. We have all the different states here, right? And we have, for each different state, we have the murder rate, we have the rate of poverty, percentage below the poverty line, I would guess. We have the percentage that graduated high school, percentage that have some college, the percentage of single parent homes, the unemployment percentage for that state, and whether or not it's some sort of rating that rates as either metropolitan or not metropolitan. But a lot of numerical variables here, right? So I'm gonna do a scatter plot first. I want to see if there's an association between number of violent crimes. Then we also have number of violent crimes, not a percentage though. So since they're different, is it a percentage? No, it's not a percentage. So since it's not, it's a rate. It's probably a rate per million or per 100,000 or per million. So it is a rate. So I can go ahead and use that. Let's say I want to see if there's an association between the rate of violent crime and the poverty rate in these various cities. Okay, before I do that, let's plot that. Okay, and let's see graphs, legacy dialog, scatter dot, simple scatter dot, and let's see if there's an association between the rate of violent crime and the rate of poverty for each state. I click OK. Let's see how that looks. Well, it looks like there might be an association there, right? Let's take a look at this. Drop that best fit line. And yeah, it's not a very strong association. I can see because R squared is only equal to 10% over there. Not a real strong association, it doesn't look like. Well, I wonder why that is. Why it's not a better association. Let's try another one. Let's try the murder rate and the rate of poverty. Oops, graphs. Okay, instead of violent crime, let's try the murder rate. And click OK. Okay, let's see if the association is stronger here. So that looks like it's a little bit stronger association than we had before. Okay, and look, look at this one. There's an outlier up here. There's a state where the murder rate is much higher than the others. 13. Let's see what state that is. See which state has that high a murder rate. Did I get that right? Was it 13? Here it is, 12.5. That's Louisiana. And the poverty rate looks to very high there too. So let's give that a try. Let's see if that's a valid association. Okay, so it looks like there's an association, not a real strong one, but it does look like an association. Let's go ahead and actually do this calculation. I'm going to say analyze, correlate, bivariate. I'm going to move in the murder rate and the poverty rate. And I'm going to ask it to find if there is, I'm going to start with the Pearson's R value. In other words, the correlation coefficient is equal to 0. That's my null hypothesis. Or the Pearson's correlation is not equal to 0. In other words, there is some correlation between those two, or some association between those two. And let's see. The Pearson's correlation is 0.427, right? Not dissimilar than the baseball one that we did. But in this case, look at this. It's statistically significant. In other words, 95% sure that R is not equal to 0. In other words, no association at all. So that's encouraging that there is an association here. So that encourages me to go further with this. Okay, let's do a regression analysis now. I'm going to say analyze. I'm going to go to regression, and I'm going to go down to linear regression. We're assuming it's a linear association. So now, what would cause what? Would the murder rate cause the rate of poverty, or would poverty be one of the causes of the murder rate? Well, I'm thinking the rate of poverty might be one of the things that contributes to the murder rate. So I'm going to make poverty my independent variable or predictor variable, and the murder rate my dependent variable or my result variable. Okay, so I'm going to go ahead and actually do this analysis. Click OK. Okay, let's see what I get here. So what I get here, when it does the analysis, I get for my ANOVA, I get less than 0.02. I also notice that when I go down here to my coefficients, right, I see, for instance, I see that the slope of the line of regression is 0.365. Here's my coefficients here. The slope is under poverty. The rate of poverty, 0.365. And my y-intercept is 0.432. Well, let's see if that's significant. Well, in fact, my 0.365 is statistically significant. Well, my y-intercept, though, may not be, but to tell you the truth, it may not mean much because I'm never going to have a situation where the poverty rate is zero or the murder rate zero in any of these states, because it may not be as relevant as our poverty rate is. So I'm going to stick with this. I'm going to go ahead and do this analysis. So what does this tell me? This tells me that the line that we just created can be described as 0.365 times the poverty rate plus 0.432 is equal to the rate, the murder rate. Okay, so let's see, 0.365. Is that right? Did I get that right? Okay, yeah, there's our 0.36x plus 0.43. Okay, so let's take, this is the formula that we've created. Y represents our murder rate is equal to 0.43 plus 0.36, I think it was 2, times our X is our rate of poverty. So we can use this line, this formula, to describe the influence that the poverty rate has on the murder rate. So in other words, if, for instance, the rate of poverty fell 5%, it would suggest 5, right? If that's 5%, that would you get 5 times that 0.36 is roughly 2. 5% reduction in the rate of poverty, 5% from the original to the final rate of poverty, would suggest a drop in the murder rate of 2%, whatever that rate is, whether it's a percentage or something like that, right? So I'm not actually, it's not 2%, obviously. It's 2 per whatever the number is, 2 per 100,000, 2 per 10,000, or something like that. We don't really know. We don't have the background for this data. But we can see that this is the rate at which we have some influence on the murder rate. Okay, so it's a predictor. So in fact, I could actually ask you, well, what if there was a municipality or a state or city where the murder rate was known, where the poverty rate is known to be 11%? What would we predict the murder rate to be? So in that case, we would say 11%. We would expect the murder rate to be around 4 per 100,000 or 4 per 10,000, whatever rate that stands for. So that's kind of the way that we would use the line of regression, and also to analyze how much a change in our independent variable would affect our dependent variable. So we can see if we do something that'll have an effect on our independent variable, we can see how well that we can predict how well that's going to perform in reducing or increasing our independent variable, our dependent variable, right? So that's one of the things we're really interested in, because, for instance, if we start a job program in there, we know and we have some idea what the cost of it might be, and we're hoping it'll impact the murder rate or the violent crime rate. Well, based on what we think we can do in terms of investment in these communities to reduce the poverty rate, it'll help us predict how it will how it will affect the murder rate. On the other hand, if our target is reducing the murder rate, Perhaps we'll find that investments in policing or investments in education may be more effective than the poverty rate because the slope will be bigger. In other words, the change in those, smaller change in those will affect the same change or a better change in the outcome that we're looking for. Okay, so that's a number of ways that we could go ahead and do this. Now, one of the other things you want to take a quick look at here is when you run your regression, you're going to wind up with a table that gives you not just R, as we predicted it before from the correlation, but also R squared. And R squared in this case says, let's see, 4.427 squared, the multiplied by itself is 0.18. That R squared represents the amount of the influence of the rate of poverty on the murder rate. In other words, 18% of the variability in the murder rate in these communities can be attributed to a variability in the rate of poverty, right? So, 18% of that variability, the murder rate is attributed to poverty. That means 82%, 82% is attributed to other factors, right? So there may be other factors here that we're looking at in this data set that may have a bigger influence on the rate of murder. In fact, we may also be interested in seeing if we combine more than one of these factors in what's called a multiple regression, right? Then we might be able to find that if we combine the poverty rate along with, say, the rate of high school graduation or the rate of college or the percentage of single parent homes, we might find that we have much better predictor. In other words, increase the size of that I square by combining those two factors to predict what the violent crime rate or the murder rate might be if we manipulate them. Okay, so I'm going to save that for Saturday. We're going to go for about an hour. I'll save that for Saturday, and we'll take a look at multiple regression on Saturday. Also, I'm going to maybe talk about how we can restructure some of these data, some of these variables, so that we can do a little bit more, get a little bit more out of them. For instance, if we have numerical variables and we're interested in doing chi-square or odds ratio with numerical variables, how you can convert a numerical variable into groups, into a new variable which is categorical with different groups. Or if you have a pair of categorical variables and you want to be able to, and it produces a larger table than a 2x2 table, how you can separate that into variables that will allow you to produce a 2x2 table, a series of 2x2 tables that will allow you to calculate odds ratios for different comparisons to those groups, right? So maybe we'll hit on that on Saturday as well. So, okay, good night, and hopefully we'll get together on Saturday morning and take another